Every day, thousands of smartphones leave this highly automated factory. But each phone begins with components smaller than a grain of rice. Hundreds of precision parts must work together inside one thin device. Robots assemble, inspect, and test each stage with microscopic accuracy.
This is the complete journey from microchips to a finished smartphone. Production begins with controlled receiving of thousands of sensitive electronic components. Every incoming batch is linked to a traceable production record.
Technicians inspect packaging before sensitive components enter storage.
Machine vision checks dimensions, contact surfaces, and visible damage. Moisture-sensitive components remain inside controlled dry storage systems.
Automated storage retrieves the exact reel required for each production order.
Bare circuit boards are checked before any component is attached.
Microscopic copper pathways will carry power and data across the phone.
Precision machined frames are measured for flatness, openings, and surface quality. Every opening must align with components installed much later.
Electrostatic control begins before technicians enter the production floor. Grounding protects microscopic circuits from invisible electrical discharge. The selected components are grouped for one controlled production batch.
A final verification prevents the wrong component from reaching the assembly machine. The factory is now ready to build the phone's main electronic system. Bare circuit boards enter the surface mount assembly line.
A thin stencil aligns thousands of microscopic solder locations. Solder paste is printed onto each contact pad in a single controlled pass.
The stencil lifts away, leaving a precise solder pattern behind. Three-dimensional inspection measures solder height, area, and position.
Incomplete or misplaced deposits are corrected before component placement.
Approved boards enter the high-speed component placement system.
Robotic nozzles collect, rotate, and place thousands of tiny passive components.
Each component is visually checked before placement.
Microscopic alignment determines whether the final circuit will function. A second machine installs larger and more complex electronic packages. The main processor requires especially precise handling.
Vision alignment places the processor directly over hundreds of hidden contacts.
Memory and communication modules form the phone's central computing platform.
Miniature connectors will link the circuit board to every major module.
Inspection confirms that every part is present before permanent soldering.
Misaligned components are corrected before heat locks them in place. The populated boards now approach the soldering process.
Reflow soldering joins every component to the circuit board. The temperature rises gradually to protect sensitive materials. Solder melts and formed electrical and mechanical connections.
Controlled cooling stabilizes the newly formed solder joints. Automated optical inspection searches for visible assembly defects. The system checks orientation, solder shape, and component presence. Specialists verify defects that require human judgment. X-ray inspection reveals connections hidden beneath major chips. Hidden solder joints are checked for bridges, voids, and incomplete contact.
Electrical probes test power pathways and circuit continuity.
Voltage, resistance, and communication paths are measured automatically.
The board is powered for the first time before entering the phone.
Failed boards enter diagnosis instead of continuing to final assembly.
Approved mainboards now move toward camera, display, and battery assembly.
Camera modules are prepared and tested before entering the phone.
Lens surfaces and electrical connectors receive a complete visual inspection.
Optical targets test focus, color response, and image sharpness.
Internal actuators are tested for fast and accurate focusing.
Stabilization systems compensate for controlled movement during calibration.
Display modules undergo separate inspection before assembly.
Uniform color fields reveal dead pixels and brightness variation. A robotic stylus tests touch response across the entire surface.
Laser measurement confirms flatness and dimensional accuracy.
Every battery cell is inspected before entering the device. Cameras check cell shape, surface condition, and connector alignment.
Electrical tests confer voltage and internal resistance.
Thermal imaging identifies abnormal heat before assembly.
Precision adhesive systems prepare for module bonding.
A continuous adhesive path is applied around the display opening.
Machine vision aligns the display before bonding. Uniform pressure creates a stable bond across the full surface. Vacuum treatment removes trapped air from the bonded assembly.
Battery adhesive is applied only to approved support areas.
The battery is placed flat without bending or excessive pressure.
The prepared frame now enters the main assembly line.
The tested mainboard is positioned inside the frame.
Locating features ensure precise mechanical alignment. The primary camera module is installed without touching the lens surface.
Additional cameras enter dedicated positions around the main board.
Flexible camera cables connect directly to the main circuit board.
The lower speaker is seated against a controlled acoustic seal.
The vibration motor is isolated to prevent unwanted mechanical noise.
Charging and microphone modules align with the lower frame openings.
A flexible interconnect carries power and data through the device.
Antenna elements occupy carefully controlled positions around the frame.
Internal switches connect the external power and volume controls.
The display cable links the screen to the main board.
The battery connection is completed only after internal assembly.
Vision inspection confirms that every connector is fully seated. Thermal materials help transfer heat away from critical components.
A shielding plate protects circuits and supports heat distribution.
Each screw receives a specific torque and tightening sequence.
Automatic torque control prevents loose joints and damaged threads.
A final internal inspection occurs before the phone is sealed. Filtered air removes particles that could remain trapped inside. The assembled phones now move toward sealing and final closure. A continuous perimeter seal prepares the phone for closure.
Vision systems verify that the sealing path remains continuous. The rear cover is aligned before it touches the adhesive.
Controlled pressure bonds the rear cover evenly to the frame.
Dimensional inspection checks thickness, alignment, and edge gaps. The assembled hardware now receives its operating software.
Each phone performs its first controlled startup.
Firmware and calibration data match the phone's installed hardware.
Optical sensors calibrate display brightness and color balance.
Camera calibration aligns focus, color, and image geometry.
Acoustic chambers calibrate the speaker and microphone system.
Shielded stations verify wireless communication without outside interference.
Every finished phone enters a comprehensive functional test. Button force and mechanical response are checked automatically. Touch sensitivity is verified across the entire display. Camera performance is checked under several lighting conditions. Air pressure testing detects microscopic leaks in the sealed enclosure. Sample units undergo validated water resistance testing.
Controlled drop tests evaluate structural durability on selected samples.
Vibration testing simulates repeatal movement during transport and daily use.
Environmental chambers test performance across changing temperature and humidity.
Final inspection checks every visible surface before packaging.
Approved phones enter clean, unbranded packaging prepared for distribution.
Automated logistics prepares thousands of finished phones for worldwide shipment.
Hundreds of components have now become one precise, connected device.
Subscribe to Full Factory Process Atlas and tell us which futuristic factory we should explore next.